Hello YouTube, RJ. I've got a little circuit I threw together on the breadboard here, and I want to talk about a phenomenon you've probably never heard of. But we're going to start out with something you've probably heard of and work into the phenomenon you likely might not be familiar with. And everybody messing around electronics probably should know about this. Let me jump over on the computer and show you a schematic of this little circuit so we can talk about what we're going to do. And then we'll come back over here, do a little experiment, and then we'll change it up and we'll go into what I want to show you today. Okay, here we are on the computer. We're in LT Spice. I just drafted up the circuit for you a little here. And let's look at what we have. Well, first of all, we've got a voltage source. This will be my power supply. I'll be able to vary the voltage to the circuit. Once you leave my power supply, it'll be clipped across a pair of 1 meg resistors. And the main device that's under test at the moment is what's called a variactor or a varicap. All diodes have capacitance, and they will vary if you apply a DC bias to them, but they vary very little. A varicap or a variactor, whichever name you want to use, they're a special diode designed to have more capacitance and to vary more with this bias. Where we often use these are in voltage controlled oscillators. By being able to apply a voltage across this and having the capacitive change, it can replace your variable capacitors in your tuning circuits. This is what we've done. We've built up a little circuit here with a varicap. We've isolated it from the power supply with some pretty stiff resistance to give me quite a bit of impedance to isolate it so I'm not interfering with my readings. While I can apply this voltage across the diode, I'm reading across that diode using a coupling capacitor, a 47 nanofarad coupling capacitor, to isolate the DC from getting into my LCR meter. And I can read the capacitance of this diode, this varicap, and I can vary the voltage to demonstrate the capacitive changes on this device. So now we're going to start out with this varicap. The particular varicap we're using is an NVAM109. I'm going to pull up the data sheet for you here and let you take a look at what it looks like. And let's look at it real quick before we go over to the bench. They're also sometimes called silicon tuning diodes. Here's the data sheet for the NVAM 109. If we go down and look, you've got a lot of specs. You can see the reverse voltages of them. The 109 is 15 volts. So we want to try to stay, no more than, say, 16 volts on it. The one we're really interested in with this particular device is its diode capacitance. Okay, and it's saying at a 1 volt reverse that it's going to range somewhere between 440 and 400, here's mine right here, 109, 400 to 520 picofarad. And then it talks about its capacitive ratio, and that's how much it changes per volt you put in. But if we roll down here and find these charts right here, you can see capacitance versus reverse voltage. And this is the NVAM 109 that we're working with. And you can see where they expect you to start out at 1 volt. And you can see as you increase your voltage, the capacitance falls down, down, down. And they're claiming around 9 volts. You should see somewhere around, what are we looking at, 20, 30, about 30 picofarad, somewhere in that ballpark. So you can see the different ones have slightly different curves. So this is the one we're going to be working with. So we're going to mention, we're going to see how this looks, how this compares out. Does it seem to follow somewhat similar to this? And then we're going to switch over and work with another device under test in the same circuit, and we're going to see if you've ever noticed this or aware of this and how it applies to you when you're designing circuitry. Maybe we could use that for something. That's kind of the end run of this whole video, is I want to try an experiment, and I'm setting you up to understand where I'm coming from. So let me get back over the bench so we can do some hands-on. Okay, we're hooked up with our NVAM 109 variactor or varicap, whichever you prefer. And so now what I'm going to do is I'm going to go ahead and throw some voltage on this thing, turn the power supply on. There's 5 volts or 4 volts, and look what happened already. So let me turn that down a little. Let's go down to 1 volt. Let's go down to 0 volts. 0 volts, we're over 500. We're over 500 picofarads. But 1 volt is where they gave us our reference, and I think it was 460 to 500. We're right in the middle of that, so we're looking great. So let's start walking up the voltage a little bit. As we 3, 4, 5, 6, 7, 8, 9 was where they were pointing out, and they were showing it potentially could get down to, I think it was like 40 or 50 picofarads. I'm getting 70. I can probably go up in voltage some more. There's 10. No, I want to go over that because you're hitting that reverse voltage. So there we are. We're getting down to 70. So that's a pretty good, from 70 to like 400 and almost 70, 80. Pretty good widespread. So, you've got your 1 meg capacitor resistors, you've got your variac, and you've got your 47 nanofarad coupler to keep the DC out of my LCR meter. Now what I'm going to do is I'm going to stop the video. I'm going to make a few changes here, come back, and we're going to talk a little about the main topic of what I want to talk about today. Be right back. Okay, I decided to go ahead and bring this up, and I have modified our circuit over there, and we're going to do a little more testing. And I have changed our varicap or variactor for a ceramic capacitor. And why I've done this is the capacitive manufacturers kind of rarely show this. Only certain data sheets you're going to find this in. It's kind of like that little thing they don't want to tell you about their ceramic capacitors, but ceramic capacitors tend to do this. And a lot of it depends on the rating type of the capacitor, the category. And so Vishay is usually pretty good, and they've got it in their data sheet here for this 615R series. What we're looking for, I'm going to go ahead and zoom right on in here and really give you all a good view. What we're looking at is a chart for their capacitors showing capacitance change versus voltage. Turns out ceramic capacitors will do the same thing as a variactor. If you bias them with voltage, their capacitance change. And just as with the variactor, as I increased the voltage, the capacitance went down. You get the same thing with ceramic capacitors. And their chart here shows you at the different rating categories what you can expect. And you can see it can be quite pronounced, like in your Z5U rated capacitors. This is your rated voltage percentage. So it tends to follow not a voltage, but the percentage of the rated. And if you follow, in the case of the Z5U rated capacitor, if you take it to 100% of its voltage capacity, you could lose 80% of the capacity of your capacitor. So all of a sudden your 100 nanofarad capacitor could be 20 nanofarad. Well, that's a pretty dramatic change. You can see you can limit it somewhat, but you can't get away from it. Even the best rated of them still lose about 20%. And I think we're pretty sure we're using Y5U capacitors out of my little assortment. So we're probably going to see it reducing capacitance as much as here it's saying 65%. You would be talking 45 nanofarads. This is a known thing. I have some thoughts on it. I'm going to go over the bench now. We're going to try it out and see what it looks like. And then I'll tell you why it matters and what I'm thinking and where I'm going with this. Okay, here we are. And I've pulled out the variac and put in a ceramic capacitor. It's a 100 nanofarad. You can see it reads 100 nanofarad on our LCR. Now what we're going to do is just see how that compares. So let me go ahead and start putting some voltage into this. Let's go up 1 volt. And we don't really see much change at 1 volt. There's 2 volts, a little bit of change. 3, 4. Starting to fall now. Let's go to 5. Falling off pretty good now. 6, 7, 8, 9, 10. This is a 16 volt capacitor, so we're going to go all the way up to the rated. And there we are. And what did the chart tell us? If we went to the 100% of the maximum rated, that we'd lose about 60% of our capacitance. We lost just a little bit more than that. It looks like we lost about 64% of our capacitance. So it's a real effect, and we can actually measure it and see it. And the reason this matters is, one, I want you to know it, because if you're designing circuitry, maybe you want to put some ceramic capacitors in your circuit to take care of transients or ripple. and you sit down and you figure, okay, to get my ripple down to this, I need this much capacitance. And if you go out and buy those capacitances in ceramic capacitors and put it on there and don't take into consideration the voltage you're putting across them, you're not going to get the capacitance you were expecting. Things aren't going to work right. So you need to be aware of this so that you can judge how much more capacitance you need so that when it derates with a bias voltage, you're taking care of that problem. Now, why I'm going down this road is I've had a thought. Variactors are getting a little harder to get and they're getting pricey. Ceramic capacitors are dirt cheap. And I was just wondering, one of those RJ's thinking about things. I was wondering if I could build a voltage controlled oscillator and not use a variactor, use ceramic capacitors in its place. It'd be interesting to see if you could actually accomplish that and how effective it would be. The other thing is, it looks like variactors are more temperature sensitive changes in temperature with their capacitance than some of the ceramic capacitors. And that being true, you might actually be able to produce a more stable voltage controlled oscillator that would hold its frequency better with ceramics than with a variactor. So in an upcoming video, we're going to build a little voltage controlled oscillator. It may be more than one video, and we're going to try seeing what we can do and maybe build the same circuit or test the same circuit with a variactor and capacitors and see what we can do. So could be kind of interesting. But hey, thanks for hanging around with me on this one. I hope you learned a little something from it. It was fun to play on the bench. I sure would appreciate it if you give me a like if you enjoyed the video. But more than anything, I'll see you in the next video.